All right, listeners, get ready because today we're going deep on a paper that really makes you think about how things move at those crazy fast speeds, like relativistic speeds.
Yeah, it's pretty wild.
Yeah, we're talking about a paper that's basically challenging some of the core ideas behind Minkowski spacetime
Mm-hmm.
and how it all connects to something you might be familiar with, phased array emissions.
Which I'm sure a lot of our listeners have heard of.
But just to kind of make sure we're all on the same page, when we talk about phased arrays, we're talking about systems that have multiple emitters working together.
Right.
And they're timed really precisely.
Yeah, very carefully timed.
To create this super focused beam of energy.
Highly directional beam.
Exactly. And here's where things get really interesting.
Mm-hmm.
This paper suggests that when you look at these phased array beams from a reference frame that's moving at like close to the speed of light,
Mm-hmm.
they don't actually behave the way we'd expect them to, based on our normal understanding of relativistic aberration.
It's a very interesting challenge.
It really is.
Yeah.
So how does this paper actually go about, exploring this idea?
Well, it set up this thought experiment to kind of illustrate the concept.
Okay.
So imagine you have a phased array. It's just sitting there stationary, and it's sending out this beam along the y-axis.
Okay.
And that beam hits a detector.
All right. Pretty straightforward so far.
Now, the question is, how would an observer who's moving super fast, like at relativistic speed relative to this setup, how would they see that beam's path?
Okay, so we've got our observer just zooming past this whole setup.
Right.
And things are already getting a little weird at those speeds.
Yeah, things start to get pretty strange at relativistic speeds.
Yeah.
Now, normally when we talk about light coming from a single source, relativistic aberration makes it look like the light bends from the perspective of that moving observer.
Right.
And we have a well-established formula to calculate that bending.
Like it's a pretty standard concept in physics,
Right.
right?
Textbook stuff.
But now we're bringing in these phased arrays, and they seem to be throwing a wrench into things.
Yeah, they definitely complicate the picture.
So
Well, the key difference is that phased arrays don't rely on just one single point source of light.
okay.
They're creating that beam by very carefully timing the emissions from multiple sources.
Right.
And this timing, well, it gets really tricky when you start thinking about special relativity
Uh-huh.
and the fact that simultaneity, the idea of events happening at the same time, is not absolute.
Oh, man. So you're telling me that just by moving really fast,
Yeah.
you could actually change how that phased array beam is behaving.
That's exactly what this paper suggests.
Wow.
And the implications are pretty mind-blowing. I mean,
Right.
if you're moving fast enough, the paper predicts that the beam might not even hit the detector anymore.
Oh, okay. So hold on. We're talking about some serious mind-bending stuff here.
Yeah.
But before we go too deep into like how these deviations work and all that, I think it's worth talking a little bit about the history of special relativity and this whole idea of simultaneity.
Absolutely. It's essential context.
Yeah. Because it's not every day you come across a paper that's potentially challenging those concepts.
You're right. It's fundamental stuff.
Yeah.
We have to acknowledge the groundbreaking work of Lorentz and Einstein.
Of course.
They completely changed our view of space and time.
Yeah. They showed us that it's all relative to the observer.
Exactly. But what's really fascinating is that even within the framework of relativity,
Uh-huh.
there are subtle differences in how different theories handle the idea of simultaneity.
Okay, now that's interesting. I mean, can you give us an example of how these different interpretations of simultaneity could play out, like in the real world or in this context?
Sure. The paper brings up the work of Manzuri and Sexel.
Okay.
They developed this test theory to compare different approaches to relativistic transformations. And their work shows that even theories that seem mathematically very similar can have different ways of dealing with simultaneity.
Okay.
And when you're dealing with something like a phased array, where the timing of those individual emissions is absolutely crucial,
Right. It's all about the timing.
those subtle differences in interpretation can lead to drastically different outcomes.
So just to be clear, we're not saying that this paper is like disproving relativity or anything like that.
Right.
It's more about exploring some of the more subtle but potentially really important differences in how we understand certain aspects of it.
Exactly. It's about nuance.
Nuance. Okay, I like that.
This paper suggests that those nuanced differences in how we view simultaneity can have really observable consequences, especially when it comes to things like interference patterns, which are super sensitive to timing.
Right, because interference patterns rely on those waves interacting with each other in very precise ways.
Precisely. And what's really exciting is that this paper proposes an experiment.
Oh, an actual experiment.
Yes, to test these predictions.
Okay.
And believe it or not, the technology to do this experiment already exists.
Now we're talking. That's what I want to hear. So let's get into the nitty-gritty. How does this experiment work? What would we actually be looking for? But before we do that, I think it's worth taking a step back
Okay.
and breaking down the math a little bit, just to make sure everyone's on the same page.
That's a good idea. Let's lay the groundwork.
Yeah.
So the paper presents two main formulas.
Okay.
The first one is the standard aberration formula for light beams coming from a single source.
Right. The classic formula.
Yeah, this is the one that tells us how much the light appears to bend from the viewpoint of someone who's moving.
Okay.
The second formula is where things get really interesting.
Right. Already.
This is the formula the authors derived to predict how a phased array beam will deviate when it's viewed from a moving reference frame.
And this is different from the standard formula.
That's the key point. These two formulas actually predict different amounts of deviation for the two types of beams.
Whoa. Okay. So we're not just talking about some theoretical difference here.
No, this is concrete.
There's a real mathematical prediction that, if it's true, could have some pretty big implications.
It could change our understanding. And the paper takes it even further. They suggest that if you get close enough to the speed of light, that formula for the phased array beam deviation starts to suggest that our simple interference model might break down.
Okay, now that's what I call pushing the boundaries of physics.
Right.
But before we jump into this experiment, I think it would be really helpful to try and visualize this paradox.
Yeah, let's paint a picture.
Like, what does this actually look like?
The paper has some figures that can help with that.
Huh?
They show the paths of both types of beams, the single source and the phased array.
All right.
And they show those paths from both a stationary viewpoint and a moving viewpoint.
Okay, so if we were looking at those diagrams, what would we see?
You'd see that the beam from a single source bends in a certain direction because of that standard relativistic aberration that we talked about.
Right.
But the beam from the phased array would actually be bending at a different angle.
Real?
And that difference between those two angles, that's what the authors are proposing to measure.
Okay, so this isn't just about, like, competing effects or something.
Oh, it's more fundamental.
This is a fundamentally different way that the phased array beam is behaving compared to a single source beam.
It all comes down to that subtle but crucial difference in how we understand simultaneity when things are moving at relativistic speeds.
And if this experiment can confirm these predictions,
It would be huge.
yeah, it would raise some really big questions about how we understand wave phenomena in general.
It would be a paradigm shift.
Okay, I'm definitely hooked.
Dude,
This is all incredibly fascinating and potentially groundbreaking.
I agree.
So let's move on and talk about how we can actually test this in the real world.
Let's get practical.
Yeah, no more thought experiment.
Time for real-world science.
Exactly. So how do we actually observe these differences in beam deviation?
Well, the beauty of this experiment is that it's actually quite simple in principle.
Okay, tell me more.
Imagine a lab setup. You've got a phased array emitter at one end,
Okay.
and you have a very, very sensitive detector at the other end.
All right, and this detector needs to be able to measure the angle of the incoming beam with, like, incredible precision, right?
It has to be extremely precise.
Okay.
Now, to introduce the relativistic element instead of, like, putting our detector on a spaceship or something.
Right, because we can't really do that.
Not yet, at least.
Yeah.
We can just move the emitter really fast.
Okay.
Think of it like a high-speed train carrying the phased array.
Ah, so we're creating the relative motion by moving the emitter instead of the detector.
Exactly.
That's clever.
And it's experimentally advantageous, too.
How so?
Because remember, we're not trying to measure absolute time differences, which would require super accurate clock synchronization.
Right, which is a nightmare.
Exactly, a major headache.
Yeah.
Instead, we're just measuring relative angles.
Ah, okay, that simplifies things a lot.
Much simpler.
So what kind of speeds are we talking about here to actually see a measurable effect? Do we need to get, like, really, really close to the speed of light?
Not necessarily.
Okay.
The paper says that even at speeds around 0.3 C,
0.3 C.
yeah, which is 30% the speed of light,
Right.
the difference in beam deviation between the standard formula and the phased array formula should be detectable.
So we're not talking about some impossible speed.
Yep.
This is something we could actually create in a lab.
It's within our technological reach.
That's amazing.
And as we push towards even higher speeds, the effect becomes more and more pronounced, so we can test these predictions with even greater accuracy.
This is really exciting stuff.
It is.
But I'm sure there are challenges in setting up an experiment with this level of precision. I mean, we're talking about relativistic speeds and measuring these tiny differences in angles.
Oh, there are definitely challenges.
What are some of the biggest hurdles we'd need to overcome?
One of the biggest challenges is the precision of the phased array itself.
Okay.
We need incredibly precise control over the timing of those individual emissions to create a truly coherent beam.
Right, because any imperfections in that timing could mess up the results.
Exactly. Even tiny variations can introduce errors.
Wow, so it's like a super delicate balancing act.
Precisely.
Are there other challenges?
Yes. Another big one is accounting for all those external factors that could influence the beam path.
Like what kind of factors?
Things like gravitational lensing, where gravity bends light,
Right.
or distortions caused by the atmosphere. Even vibrations in the lab itself can throw things off.
So all those real-world gremlins that physicists always have to battle.
Exactly, those pesky gremlins.
Yeah.
We'd need to design the experiment very carefully to minimize these effects.
Right.
And isolate the purely relativistic component of the beam deviation.
I can just imagine teams of physicists huddled over diagrams trying to predict and account for every possible source of error.
It would be meticulous work.
It sounds worth it.
It is, because even with all those challenges,
Yeah.
the potential payoff is huge.
Yeah.
If we can do this experiment and those predictions are confirmed,
Yeah.
it would be a major breakthrough in our understanding of relativity and wave phenomena.
And to be clear, even if those predictions aren't confirmed, the data we gather would still be incredibly valuable, right?
Absolutely.
It would force us to go back to the drawing board, refine our theories, explore other explanations.
That's the beauty of science.
Yeah, it's all about pushing the boundaries of our knowledge.
Embracing the unknown.
Okay, so we've got the experimental setup, the potential challenges, the importance of really rigorous analysis.
Right.
But let's zoom out for a moment. What are the bigger implications of this experiment? Like, what doors could this open in terms of our understanding of physics?
That's where things get really exciting.
Okay.
This experiment isn't just about phased arrays.
Okay.
It's a potential window into the very nature of reference frames, wave phenomena, and even measurement theory.
Okay, whoa. Let's break those down one by one.
Right.
Starting with reference frames. How could this experiment change how we think about how different observers experience reality?
Well, first of all, it would be a really strong validation of special relativity. It would show that even in these really complex scenarios involving these coordinated wave emissions, the core principles of relativity still hold up.
Okay, so it's not breaking relativity.
Right. It's more like reinforcing it.
Okay.
But it could go even further than that.
I'm all ears.
By really digging into the data from this experiment, we might gain some new insights into the subtle ways that reference frames interact with each other.
Okay.
Remember those different approaches to relativistic transformations that Manzuri and Sexel explored?
Yeah.
This experiment could give us some valuable data that helps us refine our understanding of those different approaches.
Interesting. So we're not just confirming existing theories.
Right.
We're potentially refining them based on real experimental results.
Exactly. Science in action.
I like it. Now, what about wave phenomena?
All right.
I'm really fascinated by this idea that this experiment could reveal some deeper truths about how waves in general behave at these crazy speeds.
That's one of the most exciting aspects of this research.
Yeah.
If these predictions are confirmed, it raises a fundamental question.
What's that?
Do all wave phenomena,
So not just light?
know things like sound waves, quantum waves, even gravitational waves,
Wow.
do they all transform in unexpected ways when viewed from a moving reference frame?
That's a huge question.
It is.
We could be talking about a paradigm shift in how we understand wave mechanics across physics.
It's a big deal.
Yeah. Are there specific areas where you think we might see the most profound impact?
Well, in quantum mechanics, for example, we know that wave-particle duality is fundamental.
Right.
So understanding how these quantum waves behave at relativistic speeds could really change how we think about particles and how they interact.
That's mind-blowing.
And in cosmology, where
Right.
we deal with gravitational waves rippling through space-time.
Right.
This could change how we interpret those signals from the early universe.
We're talking about shaking the foundations of some of our most fundamental physics theories.
It's a very exciting prospect.
It is.
And let's not forget about the impact on measurement theory.
Oh, right.
This whole experiment relies on measuring angles instead of absolute time differences.
Yeah.
And if that approach proves successful, it could open up new possibilities for measuring things that have been traditionally really difficult to pin down.
Can you give us an example?
Sure, one that comes to mind is the one-way speed of light.
Ah, the one-way speed of light.
Yeah, it's been notoriously difficult to measure.
Yeah, because you need incredibly precise clock synchronization.
Exactly.
But by focusing on relative angles, like in this experiment,
Right.
we could potentially get around those challenges.
Like a clever workaround.
Okay, so we've got reference frames, wave phenomena, measurement theory,
Mm-hmm.
all potentially impacted by this one experiment.
It's a lot to consider.
That's a lot to unpack, and it really highlights how interconnected these seemingly separate areas of physics really are.
They're all intertwined.
This experiment has the potential to reveal those deep connections between them.
And lead to a more unified understanding of the universe.
That's amazing. But of course, as with any scientific endeavor, there are bound to be alternative interpretations and counter-arguments.
Oh, absolutely. No groundbreaking scientific claim goes unchallenged.
Right, and frankly, that's a good thing.
It's essential.
It's what drives scientific progress.
It helps us refine our ideas.
So let's put on our skeptical hats.
All right.
And explore some of the potential criticisms that this paper might face.
Let's get critical.
All right, where do we start?
Well, one line of criticism might target the very foundation of the paper's argument,
Okay.
the nature of phased arrays themselves.
Okay.
Some physicists might argue that the paper's treatment of phased arrays as a source of truly directional emissions is a bit of an oversimplification.
So they're questioning whether those precisely timed emissions from multiple sources actually create a beam that behaves fundamentally differently from light coming from a single source.
Exactly. They might say that while the timing does create a highly directional concentration of energy, the underlying physics of the electromagnetic waves should still follow those standard rules of relativistic aberration.
So they're not denying that the beam is directional,
Right.
but they're questioning whether that directionality is really unique or if it can be explained within our current understanding of relativity.
Precisely. And that's a valid point.
It is.
It's important to remember that even in a phased array, each individual emitter is still radiating energy in all directions. The timing just reinforces the waves in a particular direction.
Okay, so that's one potential challenge to the paper's premise. What other criticisms might come up?
Another valid concern could focus on how we interpret the experimental results.
Okay.
Even if the experiment shows that the beam path deviates as predicted,
Yeah.
some physicists might offer alternative explanations that don't require us to completely rethink reference frames or wave phenomena.
So it'd be looking for explanations within the existing framework of relativity.
Exactly.
Essentially saying, hold on, there might be other things at play here that we haven't considered.
They might propose that subtle effects that we haven't fully accounted for,
Yeah.
like how the beam interacts with the atmosphere or the precise motion of the emitter,
Right.
or even tiny imperfections in the experiment itself could be contributing to that observed deviation.
So it's all about ruling out all those other possibilities
Absolutely.
before we jump to any radical conclusions.
Due diligence.
That's a cornerstone of good science.
That's fundamental.
And to be fair, the authors of this paper do acknowledge these potential criticisms,
They do.
and they even suggest ways to address them.
They're aware of the challenges.
How might they respond to these challenges?
Well, they would likely emphasize the rigor of their mathematical derivations
Okay.
and the care they've taken in designing the experiment to minimize those external factors we talked about.
Right. They're trying to control for all those variables.
Exactly.
Oh.
And they probably also point out that their predictions aren't just qualitative.
Yeah.
They're giving us specific, measurable differences in beam deviation, which would be really hard to explain away with other means.
So it's all about backing up those bold claims
Exactly.
with solid evidence and robust analysis.
Precisely.
It's like saying, look, we've thought of everything we can think of, and the results still point to something truly unique happening here.
It's compelling evidence.
And ultimately, I imagine they would welcome further scrutiny and independent verification of their work,
Of course, that's how science progresses.
because that's how we move forward.
It's a collaborative process.
Okay, so we've explored some of the potential criticisms.
Yeah.
Now let's shift gears and talk about alternative interpretations.
Right.
Are there other ways to understand these findings
Possibly.
without having to completely overturn our current understanding of physics?
There are some intriguing possibilities.
I like possibilities.
One alternative interpretation might involve taking a deeper look at the nuances of simultaneity.
Okay, so instead of saying simultaneity is wrong,
Right.
we're kind of digging into those subtleties that you mentioned earlier,
Exactly.
exploring whether there might be different, flavors of simultaneity, so to speak.
That's a good analogy.
Okay.
Some physicists might propose that what this phased array experiment is showing us
Yeah.
is a type of simultaneity that's specific to these coordinated wave phenomena,
Okay.
and that maybe this type of simultaneity behaves differently than the simultaneity we observe with like macroscopic objects.
So it's not about rejecting the whole concept of simultaneity.
Right.
It's about refining our understanding of it,
Nuance again.
recognizing that it might work differently in different physical situations.
Exactly. Context matters.
And this could lead to a more well-rounded understanding of how time and causality work in the universe.
It's a deeper dive into those fundamental concepts.
Okay, that's one alternative. What other interpretations are out there?
Another interesting possibility involves revisiting our understanding of wave propagation itself.
Okay, how so?
Some physicists might suggest that this experiment is revealing a deeper connection between something called the group velocity of a wave and its phase velocity.
Now, I know we touched on this earlier, but can you quickly remind our listeners what those terms mean?
Sure. So the group velocity of a wave refers to the speed at which the overall shape of the wave packet is moving.
Okay, like a cluster of waves moving together.
Exactly.
Okay.
The phase velocity, on the other hand, is the speed at which the individual peaks and troughs of the wave are moving.
Got it.
Now, in most everyday scenarios, these two velocities are pretty much the same.
Right.
But in extreme conditions,
Like near the speed of light.
yeah, or in complex media like those created by phased arrays, they can actually be different.
Interesting.
And this is where it gets really interesting.
Okay.
Some physicists might say that the beam deviation we see in this experiment could be due to a subtle interplay between these two velocities, something that we haven't fully appreciated before.
So it's like a hidden dance between the group velocity and the phase velocity.
Exactly, and this could lead to some really fascinating new insights into how waves travel and interact,
Wow.
especially in those extreme environments.
So we've got a lot on the table here. Criticisms, alternative interpretations.
A lot to chew on.
Can you briefly summarize those alternative explanations for our listeners?
Sure, so just to recap, some of the alternative explanations for this phased array experiment include a deeper exploration of those nuances of simultaneity. Maybe suggesting that different types of simultaneity exist in different physical contexts.
Yeah.
And a closer look at the relationship between group velocity and phase velocity at relativistic speeds.
Right.
Which could potentially reveal new things about how wave propagation works.
So instead of seeing this paper as a complete rejection of everything we know about physics,
Right.
we could view it as an opportunity to refine our knowledge.
Exactly.
To explore new ideas within the existing framework of relativity. And maybe even discover deeper connections between areas of physics that we thought were separate.
It's about expanding our horizons.
That's a great way to put it. It's a reminder that science is a process of constant refinement.
It's always evolving.
And that even our most cherished theories are open to scrutiny and reinterpretation as we gather new evidence.
That's the beauty of science.
This paper has definitely challenged us to think critically.
It has.
To question our assumptions.
And to stay open to the possibility that there's still so much we don't know about the universe.
Absolutely. And to our listeners,
yes,
we encourage you to continue this exploration on your own.
Dive deeper.
Read the full paper, check out the references, let your curiosity guide you.
Explore those ideas.
Who knows what other mysteries are out there just waiting to be uncovered in this vast and always surprising cosmos.
There's so much more to learn.
Always more to learn.
Welcome back to the Deep Dive. We're picking up where we left off, talking about how to actually test this wild idea about phased arrays and relativity.
Yeah, no more thought experiments.
Sure.
Let's talk about real-world science. How do we actually make this happen?
So the cool thing is the proposed experiment is pretty simple.
Okay, keep it simple. I like it.
Basically, you have a lab set up with a phased array emitter at one end
Okay.
and a super-sensitive detector at the other end.
So pretty straightforward so far.
And that detector needs to be able to measure the angle of that incoming beam with incredible precision.
Right, because we're talking about tiny, tiny differences in angles.
Exactly. Now, to bring in that relativistic element, we need some serious speed, but we're not going to strap the detector to a rocket or anything.
Yeah, that's not exactly practical.
Instead, we're going to move the emitter.
Okay.
Think of it like a high-speed train carrying that phased array.
Ah, so we create that relative motion by
Yeah.
moving the emitter instead of the detector. Clever.
It's more than just clever. It actually makes the experiment a lot easier.
How so?
Because remember, we're not trying to measure those absolute time differences.
Right, which would require those insanely precise clocks.
Exactly, a nightmare to synchronize.
Yeah, no thanks.
Instead, we're just measuring angles.
Right, relative angles.
Yeah, it's simple.
Okay, so what kind of speeds are we talking about here to actually see a measurable difference? Do we need to be like right up against the speed of light?
Not at all.
Okay, good,
No.
because that would be tough.
The paper says that even at speeds around 0.3 C,
0.3 C.
30% the speed of light.
Okay.
That difference between the standard formula and the phased array formula should be noticeable.
So we're not talking about impossible speeds here. This is something we can achieve in a lab.
Absolutely, it's within reach.
Exciting.
And as we push towards higher and higher speeds, that effect gets even stronger.
So we can test it with even more accuracy.
Exactly.
This is really cool, but I'm sure there are still some pretty big challenges in setting up an experiment like this.
Oh, there are always challenges.
I mean, we're dealing with relativistic speeds, incredibly precise measurements.
Yeah, it's not easy.
What are some of those hurdles we'd need to overcome?
Well, one of the biggest ones is the precision of the phased array itself.
Okay.
We need ridiculously precise control over the timing of those individual emissions.
Right. To make that perfectly coherent beam.
Exactly. Any little imperfections could mess up our measurements.
Wow. So it's a really delicate dance.
Precise.
Any other challenges?
Oh, yeah. We also have to deal with all those external factors that could affect the beam.
Like what?
Things like gravitational lensing, where gravity bends the light a little bit.
Right.
Or distortions from the atmosphere.
Uh-huh.
Even vibrations in the lab itself can throw things off.
Oh, man. It's like you can never escape those real-world gremlins.
Nope, they always find a way.
So how do you deal with all that?
It takes meticulous planning.
I bet.
We'd need to design the experiment in a way that minimizes these effects.
Okay.
And really isolates that purely relativistic component of the beam deviation.
I can picture those physicists huddled over their calculations, trying to predict and account for every possible source of error.
Yeah, it's a lot of work.
But the potential payoff seems worth it.
Oh, it is if we can pull this off.
Yeah.
And those predictions are confirmed.
It would be huge.
It would be a major breakthrough in our understanding of relativity and wave phenomena.
And to be clear, even if the experiment doesn't confirm those predictions, the data would still be valuable, right?
Absolutely.
It would force us to rethink our theories, come up with new explanations.
It's all part of the scientific process.
It's how we learn.
Exactly.
Okay, so we've got the experimental setup, the challenges, the potential impact.
It's a lot to take in.
But let's step back for a minute and look at the bigger picture.
Okay.
What are the broader implications of this experiment for our understanding of physics?
That's where things get really interesting.
I'm ready.
This experiment is about more than just phased arrays.
Okay, tell me more.
It could give us a whole new perspective on reference frames wave phenomena measurement theory.
Okay, whoa, slow down.
Oh, sorry.
Let's break those down one by one, starting with reference frames.
All right.
How could this experiment change the way we think about different observers experiencing reality?
Well, firstly, it would provide strong support for special relativity. It would show that even in these complex scenarios with coordinated waves, those core principles of relativity still hold true.
So it's not breaking relativity, it's more like reinforcing it.
Exactly. But it could go even deeper.
Oh, I like going deeper.
By analyzing that data,
Yeah.
we might learn something new about how reference frames interact with each other.
Like what kind of new things?
Well, remember those different approaches to relativistic transformations that Manzuri and Sexel explored?
Yeah, those different interpretations.
This experiment could give us data that helps us refine our understanding of those different approaches.
So we're not just confirming old theories,
Oh.
we're potentially improving them with real experimental data.
That's the power of experimentation.
Now, what about wave phenomena? I'm really intrigued by this idea that the experiment could reveal something new about how waves in general behave at relativistic speeds.
That's one of the most exciting things about this research.
It is.
If these predictions turn out to be true, it raises a big question.
What question?
Do all wave phenomena,
Not just light.
not just light things like sound waves, quantum waves, even gravitational waves,
Wow.
do they all transform in weird ways when we look at them from a moving reference frame?
That's a fundamental question.
It could change everything.
We could be talking about a paradigm shift in wave mechanics across all of physics.
Potentially.
Are there specific areas where you think the impact would be the biggest?
Well, in quantum mechanics, for example, we know that wave-particle duality is crucial.
Right.
Understanding how these quantum waves act at relativistic speeds could totally change how we think about particles and their interactions.
That's why.
And in cosmology,
Yeah.
where we deal with gravitational waves rippling through spacetime,
Right.
it could change how we interpret those signals from the early universe.
We're talking about shaking the foundations of physics here.
It's exciting stuff.
It is, and we haven't even talked about measurement theory yet.
Oh, right.
This experiment relies on measuring angles instead of absolute time differences. And if that works, it could lead to new, more precise ways to measure things that have always been super hard to pin down.
It's a clever approach.
Can you give an example?
Sure, one that comes to mind is the one-way speed of light.
Ah, yes, the infamous one-way speed of light.
Notoriously difficult to measure.
Yeah, because you need those perfectly synchronized clocks.
Exact.
But by focusing on relative angles, like in this experiment,
Right.
we could potentially sidestep that problem.
A potential workaround.
So we've got reference frames, wave phenomena measurement theory,
A lot going on.
all potentially impacted by this one experiment.
It's pretty amazing.
It really highlights how connected all these different areas of physics actually are.
It's all one big web,
And this experiment could reveal those deep connections.
leading us to a more unified understanding of the universe.
That's a beautiful thought, but of course, like with any big scientific claim, there are bound to be some alternative interpretations and counterarguments.
Oh, absolutely. No groundbreaking idea goes unchallenged.
And that's a good thing.
It's how science moves forward.
It helps us refine our ideas, address potential weaknesses.
It's all part of the process.
So let's put on our skeptical hats
Okay, I'm ready.
and explore some of the potential criticisms that this paper might face.
Let's get critical. All right, welcome back. We're wrapping up our deep dive into this really thought-provoking paper about phased arrays and relativity.
Yeah, it's been quite a journey exploring these ideas, and we've covered a lot of ground from thought experiments to proposed experimental setups, digging into the math and those potential implications for physics. But, as with any big scientific claim, there are always going to be some folks who aren't so quick to jump on board.
Oh, absolutely. Skepticism is healthy.
Right, it's crucial in science. It helps us refine our ideas, address any potential weaknesses, and ultimately arrive at a more solid understanding of how things work.
It keeps us honest.
Exactly. So let's put on our skeptical hats for a minute and explore some of the potential criticisms that this paper might face.
Okay, I'm ready to play devil's advocate.
All right, so where do we start?
Well, one line of criticism could target the very foundation of the paper's argument, the nature of phased arrays themselves.
Okay, so what are they skeptical about?
Some physicists might argue that the paper is treating phased arrays as a source of truly directional emissions is a bit of an oversimplification.
Okay, so they're questioning whether those precisely timed emissions from multiple sources actually create a beam that's fundamentally different from light coming from a single source.
Exactly. They might say that while the timing does create this really focused beam of energy,
Yeah, that highly directional beam.
right, the underlying physics of those electromagnetic waves should still follow the standard rules of relativistic aberration.
So they're not denying that the beam is directional,
Right.
but they're questioning whether that directionality is really unique or if it can be explained with our current understanding of relativity.
Precisely, and it's a valid point.
Yeah.
It's important to remember that even in a phased array, each little emitter is still sending out energy in all directions. It's just that the timing reinforces the waves in one specific direction.
Okay, so that's one potential challenge to the paper's core idea. What other criticisms might come up?
Another valid concern could be about how we interpret the results of that proposed experiment.
Okay, so even if we see that beam deviating as predicted,
Right.
there might be other explanations.
Exactly. Some physicists might offer alternative explanations that don't require us to, completely rethink reference frames or wave phenomena.
So they'd be looking for explanations that fit within our existing understanding of relativity.
Right. Basically saying, hold on, there might be other factors at play here that we haven't considered.
Like what kind of factors?
Well, they might suggest that subtle effects that we haven't fully accounted for, things like how the beam interacts with the atmosphere or the exact emotion of that emitter,
Right.
or even tiny imperfections in the experimental setup, could be contributing to that deviation we observe.
So it's like the classic scientific detective work, ruling out all the other suspects before you point the finger at the unusual suspect.
Exactly. Got to be thorough.
Yeah. And to be fair, the authors of this paper do acknowledge these potential criticisms,
They do.
and they even suggest some ways to address them.
They're ahead of the game.
So how do they propose to tackle these challenges?
They would likely emphasize the rigor of their mathematical calculations
Okay.
and the care they've taken in designing that experiment to minimize those external factors.
Right, like controlling for all those variables as much as possible.
Exactly.
Okay.
They'd also probably point out that their predictions aren't just qualitative.
Meaning it's not just a vague idea?
Right. They're giving us specific measurable differences in that beam deviation, which would be pretty hard to explain away with other factors.
So they're putting their money where their mouth is, basically.
Yeah, they're backing up their claims with hard numbers.
And in the end, I imagine they'd be totally open to other scientists scrutinizing their work.
Oh.
And even trying to replicate their experiment independently.
That's the beauty of science. It's a collaborative process.
Yeah, it's all about testing those ideas and seeing if they hold up.
Peer review replication. That's how we move forward.
Okay, so we've explored some of the potential criticisms of this paper. Now let's switch gears and talk about alternative interpretations.
Okay, sounds good.
Are there other ways to understand these findings that don't involve completely throwing out our current understanding of physics?
Well, there's some interesting possibilities.
I like possibilities.
One idea is that maybe we need to dig a little deeper into the whole concept of simultaneity.
Okay, so instead of saying that simultaneity is just plain wrong,
Right.
we're exploring those nuances that you mentioned earlier.
Exactly. Maybe there are different types of simultaneity.
Different flavors of simultaneity.
I like that analogy.
Okay.
So some physicists might propose that this phased array experiment is showing us a kind of simultaneity that's specific to these coordinated wave phenomena.
And maybe this type of simultaneity behaves a bit differently than the simultaneity we see with everyday objects.
So it's not about rejecting simultaneity altogether.
Right.
It's about refining our understanding of it,
Nuance is key.
recognizing that it might work differently in different contexts.
Exactly. Context matters.
And this could lead to a more complete understanding of how time and causality work in the universe.
It's a deeper dive into those fundamental concepts.
Okay, that's one alternative. What other interpretations are out there?
Another interesting possibility is that we might need to rethink our understanding of how waves propagate.
Okay, tell me more about that.
Some physicists might suggest that this experiment is revealing a deeper connection between the group velocity of a wave
Right.
and its phase velocity.
Now, I know we touched on this earlier, but can you remind our listeners what those terms mean?
Sure, so the group velocity is basically the speed at which the overall shape of a wave packet travels.
Like a group of waves moving together.
Right, whereas the phase velocity is the speed of the individual peaks and troughs within that wave.
Okay, got it.
Now, in most everyday situations, those two velocities are pretty much the same.
Right.
But in extreme conditions, like near the speed of light, or in complex media, like the kind created by phased arrays,
Yeah.
those two speeds can actually diverge.
Interesting.
And this is where it gets really interesting.
Okay.
Some physicists might say that the beam deviation we see in this experiment could be due to a subtle interplay between these two velocities.
So it's like a hidden dance between the group velocity and the phase velocity.
Exactly, a dance we haven't fully understood until now.
And this could lead to some pretty big changes in how we think about waves.
Absolutely, it could revolutionize wave mechanics.
Okay, so we've got a lot to think about here. Criticisms, alternative interpretations.
Yeah, this paper has sparked a lot of debate.
Can you briefly summarize those alternative explanations for our listeners?
Sure, so just to recap, some of the alternative explanations for this phased array experiment include maybe there are different types of simultaneity that apply in different situations.
Right, the different flavors of simultaneity.
And maybe there's a deeper connection between group velocity and phase velocity at relativistic speeds.
Okay.
That could change how we think about wave propagation.
So instead of seeing this paper as like a complete rejection of everything we know about physics,
Right.
we can view it as an opportunity to learn more, to explore new ideas within our current understanding of relativity.
It's a chance to refine our theories.
Yeah, and maybe even discover new connections between areas of physics that we thought were separate.
Exactly. It's all about expanding our knowledge.
That's a great way to put it. And it reminds us that science is a journey. It's a process of constantly learning and refining our understanding of the universe.
It's a beautiful thing.
It really is. And to our listeners, we encourage you to continue this exploration on your own.
Yeah, keep that curiosity going.
Read the full paper, dig into those references, let your imagination run wild.
Explore those possibilities.
Who knows what other mysteries are out there waiting to be uncovered in this vast and ever-surprising cosmos?
There's always something new to discover.
There's the beauty of it. Thanks for joining us on this deep dive, and until next time, keep exploring.